Welcome. In this video, we'll walk through a classic example of solving a system of nonlinear equations. The system we're going to tackle is the equation x squared plus y squared equals 2 and the equation x times y equals 1. By the end of this lesson, you will be able to solve for the values of x and y that satisfy both of these equations simultaneously. In other words, we're looking for pairs of numbers, x and y, that make both equations true at the same time. Our goal is to find all pairs, x, y, that satisfy both equations. Let's start with a common strategy, substitution. Our plan is to use the second, simpler equation to express one variable in terms of the other, and then substitute that into the first equation. Let's begin with the second equation, x times y equals 1. This one is easier to manipulate. From the equation x times y equals 1, we can isolate one of the variables. Let's solve for y. To get y by itself, we can divide both sides of the equation by x. This gives us y equals 1 divided by x. Now we have an expression for y. It's important to note here that we are making an assumption that x is not 0. If x were 0, the equation x times y equals 1 would become 0 equals 1, which is impossible. So we know x cannot be 0. Now for the substitution part. We'll take this expression for y and substitute it into the first equation, x squared plus y squared equals 2. Replacing y with 1 over x gives us x squared plus the quantity 1 over x, all squared, equals 2. Notice what happened. Our equation now only has one variable x. This is a much simpler problem to solve. Let's simplify our new equation and solve for x. Remember, our equation is x squared plus 1 over x squared equals 2. Here is the equation we need to solve. Our next step is to expand the squared term. The quantity, 1 over x squared, is the same as 1 squared over x squared, which is simply 1 over x squared. So, the equation becomes x squared plus 1 over x squared equals 2. Our next step is to clear the fraction. To get rid of the fraction 1 over x squared, we can multiply the entire equation by x squared. This is a powerful technique for solving equations with fractions. Multiplying everything by x squared gives us x to the fourth power, plus 1 equals 2x squared. Now we have a polynomial equation. Let's move all the terms to one side to set it equal to 0. This is a common strategy for solving polynomials. Rearranging the terms, we get x to the fourth minus 2x squared plus 1 equals 0. This is a fourth-degree polynomial. At first glance, a fourth-degree equation might seem intimidating. But take a close look at the pattern of the exponents. We have x to the fourth, x squared, and a constant. This pattern hints that we can use a substitution trick. Let's let a new variable u be equal to x squared. If u equals x squared, then u squared would be equal to x squared squared, which is x to the fourth. Substituting this into our equation, we get u squared minus 2u plus 1 equals 0. This looks much more familiar. This is a simple quadratic equation, and it can be factored. This specific form is a perfect square trinomial. It factors into the quantity u minus 1 squared equals 0. Factoring is often the fastest way to solve a quadratic. For the square of an expression to be 0, the expression inside the parentheses must be 0, so u minus 1 equals 0. This means u equals 1. We have successfully solved for u. We found that u equals 1, but we're not done. Remember, we need to find x, not u. We need to back substitute to find the values of x. We defined u as x squared. Since u equals 1, that means x squared must also equal 1. So, we have the equation x squared equals 1. To solve for x, we take the square root of both sides. Remember, when you take the square root to solve an equation, you must consider both the positive and negative roots. The square root of 1 is 1, so our solutions for x are positive 1 and negative 1. Let's call these x1 and x2. We now have two possible values for x, but for each x, we need to find the corresponding y value to get a full solution pair xy. Let's find the y values. We'll use our substitution equation, y equals 1 over x, and our two x values. Our plan is to plug each of our x values into the equation y equals 1 over x to find the corresponding y. Let's start with our first case, where x is positive 1. If x equals 1, then y is 1 divided by 1, which equals 1. This gives us our first solution pair, 1, 1. Now for our second case, where x is -1. If x equals -1, then y is 1 divided by -1, which equals -1. This gives us our second solution pair, -1, -1. We've found two potential solution pairs. The final and very important step is to check our answers by plugging them back into the original equations. We must verify our solutions. We have two pairs, 1, 1, and -1, -1, and two original equations to check against. Let's check the first solution. 1, 1. First into equation 1. Plugging in x equals 1 and y equals 1, we get 1 squared plus 1 squared. That's 1 plus 1, which equals 2. This is true. The first equation is satisfied. Now let's check it in the second equation. Plugging in x equals 1 and y equals 1, we get 1 times 1, which equals 1. This is also true. Both equations are satisfied, so 1, 1 is a valid solution. Great. Now for the second solution, -1, -1. Let's check equation 1 first. Plugging in x equals -1 and y equals -1, we get -1 squared plus -1 squared. That's 1 plus 1, which equals 2. This is correct. And finally, let's check it in equation 2. Plugging in x equals -1 and y equals -1, we get -1 times -1. A negative times a negative is a positive, so this gives us 1. Correct again. Both solutions work, so we have found all the pairs that satisfy the original system. So, let's recap what we accomplished. We set out to find the solutions to the system. X squared plus y squared equals 2, and x times y equals 1. We successfully found two unique pairs that solve this system. Our solutions are the point 1, 1 and the point -1, -1. A useful way to visualize this is to graph both equations. X squared plus y squared equals 2 is the equation of a circle centered at the origin with a radius of the square root of 2. Graphically, the solutions are the points where the circle intersects the hyperbola xy equals 1. The points 1, 1, and -1, -1 are exactly where these two graphs cross. This confirms our algebraic result. Thank you for watching.